Hey guys, today welcome to our lesson for section 6.5 graphs of trigonometric functions. So if you guys remember back to Math 111, your good old college algebra days, and we talked about function transformations, right? If you reach back in your brain, we're going to jump up a little bit and kind of do some old-fashioned refreshing notes, right? We said that if we had, say, a function g of x, and it could be represented as the transformation of its parent function, right? And overall, it was something like a times f of b times x minus h plus k. And this combined all of our transformations, our shifts, both vertical and horizontal, our vertical and horizontal scalings, as well as any reflections could all be mapped into here. Very similar ideas and concepts apply to trig functions. However, we talk about them a little differently. And so I want to get into kind of how we talk about that, how we can transform these trig functions, and how it can be used for some really cool problems. So the first thing we want to talk about is construct the graph of 1/3 sine x using known ordered pairs. So anytime we're graphing trig functions, we're always going to be in radians. That way we can go from, say, 0 to 2 pi, and we can complete a full cycle of sine and cosine. And we'll talk about what that means. It's really called a period. And so what I want to do right now is I want to refresh ourselves on what the graph of sine looked like. So if I just do a very simple grid here, so we've got 0, pi over 2, pi, 3 pi over 2, and 2 pi, right? We know that sine starts at the origin, goes up to 1, goes up to 1, comes down to 0, down to -1, back up to 0. Okay, now ignore all my terrible, drawings and stuff like that, but we can assume it goes to 1 and stuff like that. So what we have here is what we call period of sine. Now, some really easy points are all of these right here. So we've got 0, 0, pi over 2, 1, pi 0, 3 pi over 2, -1, and 2 pi 0. So I want to use those points to help us construct the graph of this y equals 1/3 sine x. So I know that if x is 0, okay, then sine of x is 0, and 1/3 times 0 is 0. I know that if x is pi over 2, then sine of pi over 2 is 1, and 1 times 1/3 is just 1/3. I know if x is pi, then sine of pi is 0. 0 times 1/3 is 0. You guys are probably getting the idea of what's going to happen here. If x is 3 pi over 2, sine of 3 pi over 2 is -1. -1 times 1/3 gives us -1. -1/3. And lastly, if x is 2 pi, again, sine is 0. 0 times 1/3 is 0. So we can use these 5 points to get an idea of what this graph would look like. Okay. And what's really kind of crazy in a good way, is that this still, looks almost the exact same. But what's the difference? The difference is that instead of coming up to 1, only making it up to 1/3, instead of going down to -1, it's going down to -1/3. And so that is how that affects our function. And so what is that called? What do we call that? How do we describe that? And what the term is that it's called the amplitude of those functions. So the amplitude of y equals a times sine of x, or y equals a times cosine of x, is half the distance between the maximum and minimum values of the function. So what does that mean exactly? Well, that means that if we take the maximum value here, 1/3, and the minimum value, negative 1/3, find that distance, the amplitude is half of that. So there's a term that's not brought up in here, and it's the midline. And that's something that is used sometimes. You'll see it some places, sometimes you won't. Midline of a trig function, specifically sine and cosine, is essentially this line about where we kind of stop, kind of the zero line, if you will, in a standard function. If it's shifted up or down, that can change where this midline's at. But what it is basically halfway between the minimum and maximum point of some horizontal line here. And so our amplitude is essentially just how far away from this midline do we go. And so this distance here is 1/3, and this distance here is also 1/3. So we can use that, and that is what our amplitude is. It's kind of how far these peaks go. So given our equations being either of these two forms, okay, we get that the amplitude is equal to the absolute value of A. Okay. So what this means is if our graph is, say, such as this example 2 here, -2 sine, our amplitude is still just 2. And so what that means is from this kind of midline, from this kind of middle, our function will go up 2 units, and then from there it'll also go down 2 units. That'll be kind of the maximum spread that our function has. Okay. The next definition that is really important to know is period. Okay. So what the period is the amount of time, in other words, kind of the horizontal distance it takes for our function to complete one cycle, to start repeating itself. If I were to come back up to this function here that we've got drawn for example 1, you can see, I'll switch over to blue there. We can see that right here is kind of where it starts, and then it comes to right here. And if we were to continue graphing this, it would just continue along doing the exact same thing. It would just be repeating what we have in here. And that distance went from 0 to 2 pi, so this has a period of 2 pi. Okay, so the way we can calculate the period for sine and cosine, so if our equations, I'll use a different color, for equations, okay, come on, are in those forms, we can calculate the period simply by saying that the period, which we'll use a capital P or lowercase p, it really doesn't matter. I know it's, they look very similar, especially on a board. Is 2 pi over b. Okay, and this is how we calculate the period. Now this is only for sine, cosine functions. Okay, tangent has a different period. We'll talk about that in a little bit when we get to dealing with tangent. But for sine and cosine, they both have a period of 2 pi. So if we just graph sine and cosine, it has a period of 2 pi. Okay. And so to graph this next function here, we need to identify a few things first. First thing we need to do is we need to identify our amplitude. And that's not necessarily something we would explicitly write out every time. It's definitely something we want to, at least in our head, go like, okay, cool. My amplitude is blank, so I know that this is going to have a max and a min of blank. Okay, so here we know that our amplitude is 2 because our A value is -2, and our amplitude is the absolute value of A, so we get -2. Now, we need to figure out what our period is. So we know by definition that our period is 2 pi over b. In this problem here, our b value is 1/4. And if you're not sure about that, the reason why is because we can write this as -2 sine of 1/4 times x. Okay. So our b value is 1/4. So we divide this by 1/4. Dividing by a fraction is the same as multiplying by the reciprocal. So instead of dividing 2 pi by 1/4, we can think of it as multiplying 2 pi by 4. And we end up with 8 pi. Okay. Now, there's one more thing I want to kind of come back with our sine function and talk about. This just isn't something that we really utilize as far as practically or as far as theoretically or anything like that. But it's a very useful practical tool to help work with these things. Notice that up here on this graph of example 1, I'll go with green, we split into 1, 2, 3, 4. So we split our period into 4 pieces, and that gives us our nice values of the high point, midpoint, low point, midpoint. Okay, and so by doing that, by splitting our period into 4 pieces, we can identify kind of the ideal increments to assess our function at. And so since we want to split it into 4 pieces, we just simply, to figure out what the increments we're going to use, we just simply take our period divided by 4, and so that gives us 2 pi in this case. So what that means is we're going to look at the points 0, 2 pi, 4 pi, 6 pi, and then one full period is 8 pi, so that's the highest we're going to go up to. So we want to look at these values just the same way that on this first example we looked at 0, pi over 2, pi, 3 pi over 2, and 2 pi. And so that's how we want to deal with this. So the next thing we need to do is we need to assess what our start and end points are. And that's really going to be important and crucial in our next, after we gain one more piece of knowledge here. It's not really going to be affected by this graph, but it is something we want to kind of start practicing. And so we know that normally these functions starts at 0. The cycle of the function starts at 0 and ends at 2 pi. So what we want to do to figure out the start point, okay, is I want to take what is inside of our sine function, and I want to set that equal to 0. So I'm going to take x over 4 and set that equal to 0, and that's true when x equals 0. And then I want to find our end point, okay, I want to take our x over 4, set that equal to our 2 pi, and that gives us our 8 pi. And lo and behold, that's where we're starting, and that's where we're ending, okay? So that will give us this will give us a graph of one period of this function, okay? So what I want to do is I want to figure out what these values are. So if x equals 0, what is y? Well, if x is 0, okay, follow with me, then we have negative 2 sine of 0 over 4. So 0 over 4 is 0. Sine of 0 is 0. Negative 2 times 0 is 0. Well, that's nice. This still starts at 0. Okay, so I'm going to get a graph going. So now we have 0, 0, 2 pi, 4 pi, 6 pi, 8 pi. Now, if x is 2 pi, so then we have, inside the sine function, we have 2 pi divided by 4, which gives us pi over 2. Sine of pi over 2 is 1. 1 times negative 2 is negative 2. So then we get the point 2 pi, comma, negative 2. Okay, and we're going to continue doing this pattern for all of these points. And so at 4 pi divided by 4 is pi. Sine of pi is 0. 0 times negative 2 is 0. Now we do the same with 6 pi. So if x is 6 pi divided by 4 gives us 3 pi over 2. That's what it reduces to. And we know the sine of 3 pi over 2 is negative 1. And negative 1 times negative 2 gives me positive 2. And lastly, 8 pi. 8 pi divided by 4 gives us 2 pi. Sine of 2 pi is 0. 0 times anything is 0. We're back here. So we're still starting at the origin, but instead of going up this time, we are going to go down, back up. Okay. And if you notice, that looks very similar to the sine function, except instead of the sine function normally went up, then down, this went down, then up. And that's very simply just because of the negative on that amplitude. If you remember back to algebra, to college algebra, right? If that a value was negative, that was just a vertical flip. And that's all we're dealing with here, is our function has been flipped vertically. In other words, you can think of the y-axis kind of being flipped over on itself. Okay. Now, if you wanted to, you could continue and graph more of this function, right? You would just label these things appropriately. Okay, so this point here would be negative 2 pi, negative 4 pi, negative 6 pi, negative 8 pi. And now what you're looking at is I have now graphed 2 periods of this function. So that's something that you're going to need to be very aware of, is what the question is asking you to do. If I just say to graph the function, as long as you get 1 period, you're good, right? Don't say, oh, graph sine. Sure, it's like that. That's part of a sine function, right? You need to at least give me enough that I know that you know what you're doing. So when you're graphing a trig function, you always have to graph at least 1 period. And most of the times, especially like on a test, to avoid any confusion, I will specify, I will say, graph 2 periods of this function. Make sure if I say to graph 2 periods that you actually graph 2 periods. Otherwise, you'll lose points. Okay. Let's move down to definition 3. So this gives us kind of all of our characteristics. So if you notice, the definition, or these kind of general forms here, let's do green. Okay, these general equations here look very similar to what we had when we talked about function transformation in college algebra, right? We've got this little a here, we've got the b here, we've got that x, that. And if we look down here, right, that's exactly the same. The difference is, instead of saying some arbitrary parent function, it's specifically stating the sine and cosine functions. Okay. So as stated before, our amplitude is absolute value of a, and our period is 2 pi over b. That hasn't changed. But this c here gives us something that we call the phase shift. Okay. Just like in college algebra, in transformation, function transformation, those phase shifts can be kind of counterintuitive. If you see something where you say have x plus pi over 6, our natural intuition would say that moves us in the positive direction, but actually moves us in the negative direction. And that is entirely because of this being defined with that minus there. Okay. Because we have x minus c. So when we have x plus pi over 6, what we really have is x minus negative pi over 6. And so our phase shift, c, is negative pi over 6. D is just very simply the vertical shift. Much like it was in 111 or any other class before, this d value does what we think it does. If it's plus 3, it moves our entire function up 3. If it says minus 3, it moves the whole thing down 3. What's really important when you're kind of keying in on this is it's really useful to think about the midline of the function. So you can think about d moves our midline, a changes how far away our peaks and valley go from the midline, and then b changes kind of how fast it kind of reaches those peaks and valleys, and c moves it left and right. Okay. So if we put all of this together, we can make this work. Now, in example 3, we're not gonna have to deal with the an alternate period, because notice the b value is 1, so it's nice and easy for us. We will have to deal with that in a minute, and I want to talk about that when we get to it. But right now I want to make a note. Notice how this is written out. It is b times parenthesis x minus c. So you have to be very careful when you're looking at the phase shift and your period, making sure that it is actually in this form and that it's not written as like a bx minus c. Okay, it needs to be written as b times the quantity x minus c. And we'll talk about how to deal with that here in a little bit. It's really easy, you just factor. Okay, so what I want you guys to do right now is I want you guys to look at this example 3. So y equals 3 cosine of x plus pi over 6. And I want you guys to identify the amplitude, the period, the phase shift, and the vertical shift. Okay. If there is none, right, then you need to identify whether or not it's appropriate to say none, or if you need to say something else. So like if there is no change to the period, it's not that there's no period, it still has a period, but what is that period? So I want you guys to pause this video and I want you guys to just identify those things, okay? Period, phase shift, amplitude, and identify if there's a vertical shift. If there is, what is it? Okay? All right, pause it and go. Come on, I'm drinking my coffee now, you guys. Pause the video. You can't see me, so I have to make a very loud slurping sound so you know I'm actually drinking my coffee. All right, so hopefully you guys have done that. If you guys haven't done that, seriously, pause the video right now. Do it. I know you're like, it's a video, you're not really here, it doesn't really matter, but it does. It's getting you practice. Okay. So let's look at this. So what's our period? Let's identify that first. Our period, well, we know that's 2 pi over b. What's our b value in this problem? Okay. Notice we're dealing with cosine, not sine, right? The last two examples have both been sine. Okay. Now we're dealing with cosine. But sine and cosine both have the same period. They both have a period of 2 pi. And so we're able to use p equals 2 pi over b to calculate that. Now our b value here is simply whatever the coefficient is right here. And notice there isn't one, which means it's a 1. So it's just 2 pi over 1, which is just 2 pi. So our period is just 2 pi. Easy enough. Now, phase shift, there's a couple ways you can talk about that. Our phase shift, you can say that, you can say what the C value is, but a better way, a more descriptive way, is to describe what that phase shift does. And so here we can identify our C. So C in this problem is equal to negative pi over 6. And we know that because our function is defined as x minus c. So since we have x plus pi over 6, the only way that we can have minus become a plus is if it's negative. So what does this do? Well, a phase shift, a c value of negative pi over 6, this would shift the graph. Now, since it's a negative value for c, okay, it's going to be going in the left direction. And you may be like, wait, you said counterintuitive. That applies to the function itself. Okay, so that was plus pi over 6, so that's the kind of counterintuitive. So it shifts the graph left pi over 6, if you want to, units. Okay, and we can see that when we look at kind of identifying our start and end points. Okay, so our start point, right? We take whatever's inside of our trig function. And since we know cosine starts at 0, we set this equal to 0. Just subtract pi over 6. And we get that x is equal to negative pi over 6. If we look at our endpoint, right, we take our thing inside of the trig function and we set it to what the period ends at, which is 2 pi. subtract pi over 6. We get that x equals 11 pi over 6. And so we can kind of figure out, we can see from that, oh, hey, this shifted us. It was from 0 to 2 pi, and now it's negative pi over 6 to 11 pi over 6. So that shifted left. So hopefully that helps. Amplitude is pretty easy. If I can ever write it. Our amplitude is equal to, very simply, 3. Okay, awesome. Now, what are our increments? Well, remember, to figure out our increments, we want to very simply take our period, in this case it's 2 pi, and divide it by 4. And that's just going to be pi over 2. So what that means is we know where we start, we know where we end, and I want to take steps of pi over 2 so that I can stick with kind of getting our midpoint, high point, low point ideas. And so our points are going to be negative pi over 6. And then if I add pi over 2 to that, I would go to pi over 3. I add pi over 2 to that, I get 5 pi over 6. If I add pi over 2 to that, I get 4 pi over 3. And lastly, I get up to my 11 pi over 6. And so now what's left is to use these inputs, substitute them into our function, and evaluate what we get. So what happens when I have an x value of negative pi over 6? Well, I get negative pi over 6 plus pi over 6. All right, I'll write this one down just because as I was talking through it last time, I kind of felt a little confusing maybe. Negative pi over 6 plus pi over 6, right? This here gives me 0. So we get 3 cosine of 0. Cosine of 0 is 1. 3 times 1 is 3. Okay, and we do the same thing for all 5 of these points. So if we have pi over 3 and for x, we add pi over 6, take the cosine of that, multiply it by 3, we get 0. Negative 3, 0, 3. Which, for those of you who've forgotten what cosine looks like, okay, so sine started at the origin, went up, then down, then back up. Cosine starts up at 1, okay, goes down and up, okay. And if we look at this function and these points, we start at 3, go to 0, go to negative 3, go to 0, back up to 3. That makes sense. That matches with what we would kind of think of what we would do. Okay. So negative pi over 6, pi over 3, 5 pi over 6, 4 pi over 3, and 11. 11 pi over 6. So I start at 3. We have that. Now, that's a fairly quick drawing. It's not super curved, but that's okay. Especially in this class, I would totally be okay with something like that if you wrote it. We could kind of extend a little bit to show that it's going to turn and come back down, whatever you want to do. All right. So let's move on to a more complicated example. So we know that the kind of parent definition function, right, was y equals A sine of B times quantity x minus C plus D. We're not in that form. Right? Now our issue comes inside of the sign. And this is how most functions would be written, right? You wouldn't really write a function like this. You would write it like this. But to be able to identify our period and our phase shift, we need to rewrite this function in this form. Let me see. Just to save room, just in case I don't want to run out of room, I'm going to do this above. So we get -2 sine. So all I have to do to get it into this form is I just factor out the pi over 6 from the piece inside of our sine function. So I get pi over 6 times x minus 3. And then we have our plus 3. So what happened there is if I divide pi over 2 by pi over 6, I just get 3. Ooh. And so that is kind of how we want to handle something like that. Okay, minus minus 3. So what's really nice is we can use all of the things we have to do this. So our phase shift is just 3. Again, because we have accounted for the minus by factoring that out. So we have an x minus c, which is exactly what we have. So what this is happening is we're being shifted to the right 3 units. Now our amplitude is just absolute value of 2. That's just 2. Easy enough. Now what about our period? Well, to find our period, we need to know what our b value is, and we need to know what the period of the parent function is. So our parent function is sine, period is 2 pi. So our period, p, is 2 pi over 6, which just comes to a lovely 12. Okay. So that means once we figure out where we start and where we end, we know our increments will be 12 divided by 4, and that's just 3. Okay, so we're almost ready to start figuring out these points. Okay, we need to find where we start and where we end. So again, just like normal, our start point, we have to solve when pi over 6x minus pi over 2 is equal to 0. Now, this is some pretty straightforward algebra using fractions, right? We add pi over 2, divide by pi over 6, simplify things, and we end up with x equals 3. Our endpoint, okay, we just need to solve when pi over 6x minus pi over 2 equals 2 pi. We get that x is equal to 15. Now, for those of you who are thinking like, why do I have to do these start and end point equations every time? You don't, absolutely not, right? There's some really cool things that we can do. We can actually really combine 2 pieces and identify our start and end point. We can use the phase shift along with the period of our function to identify the start and end point. We know that a sine and cosine functions start at 0. And so I need to use my phase shift. That tells me where to start at. So if I normally start at 0, but my phase shift is 3, so I'm moving to the right 3 units. So that means instead of starting at 0, I'm going to start at 3. And then I know that the period of this function, of this new function here, is 12. So if I'm at 3 is where I start, I need to go 12 more. That's where my thing is going to end. And 3 plus 12 is 15. And so you can identify your start and end points that way as well. I just want to go through it algebraically because that's kind of one of those nice things that if all else fails, algebra works. Now, let's get our pieces. So we know our increment is 3. We start at 3, end at 15. So we're going to go 3 something, 6 something, 9 something, 12 something, and 15 something. Now, it's going to be really tempting on something like this to jump in with like zeros and ones and stuff like that. But, we have something else in here that we haven't had in our other functions. And that is a vertical shift. Okay. Now, I didn't ask you to identify it, and you don't really have to. You could just kind of, plug 3 in for X, evaluate, and see what comes out. But I want to actually use that vertical shift to help us identify what's happening. So that vertical shift is this. That vertical shift is from that 3 right there. So that means our vertical shift goes up 3. So what we can think about is that normally takes what would have been the midline of our sine function and moves it up 3. So in a normal sine function, our midline is the x-axis. So by having this one shifted up 3, okay, what that does is it changes our function. Try and mirror a little better. So that this point here is 3. Okay, so it just moves that midline up 3 units, and then everything else kind of acts the same. Same thing happens here. So we know normally at the start of our sine function, we are at 0. That doesn't matter what the amplitude is, doesn't matter what the phase shift is, doesn't matter what the period is. Wherever we start our function, wherever we have identified our start point at, that's going to have an output of 0. But here we have this vertical shift up 3. So it goes from 0 and you go up 3 and you get 3. Pretty nice. Now, if we think about the next step, there's a lot of ways we can think about this. One thing is plug 6 in, use your calculator, evaluate this, and you'll get a point, and it's super easy. But if I just want to think through what's happening here, so sine, if I'm going to go all the way back up to the top, okay, and look back up here at our regular sine function, right? Our first step, we were at 0. Our second step, right? Let's come up one more. Our second step, we're at 1, okay? So if I come back to our problem that we're working on, our second step, we would be at 1, except we have this phase shift up 3. Oh, but wait, it's also our amplitude is 2, but it's also got a negative. So all of these things are happening. And so what basically is saying, so just looking at this, seeing this negative, that tells me I know my function, instead of doing what it normally does, is going to be flipped. That means at that first step, I'm going to go to -1. But my amplitude is 2, so I'm really going to go to -2. And then that's going to get moved up 3 with this vertical shift. So I know this is kind of seeming like a lot. I'm going to slow myself down. Okay. So I know normally our function at the second point would go to 1. But because our a value here is negative, I know that flips it over, so we know we're going to -1. But because our amplitude is 2, I know I'm actually at -2, not -1. Okay. And then the last thing we have is this vertical shift up 3. So if I'm at -2, I actually go up 3 from there, and I get 1. Okay. Now what's really cool is no matter what, we know the next step, the third step, okay, the third point, right? Start, first point, third point, or second point, I guess, second, if we call that the start, is the same as the start point. Doesn't matter whether it opens up or down, whether it's been shifted or anything like that. So I know this is going to be back at 3. And what's even better is I know it ends at the same spot too. So I know that's 3. Now, in the past, we've just been able to be like, you could think of, okay, well, this 6-1 here, so this is going to be opposite, so it can be 12 -1. But the problem is we have this vertical shift, so it's not exactly correct. But this is where thinking of the midpoint is really nice. So our midpoint for this problem is at 3. Our amplitude is 2, which means I know from this midpoint of 3, I'm either going to go up 2 or down 2. We already figured that this one here went down 2, so that means this one here must go up 2. Now that's a whole lot of kind of critical thinking and reasoning and stuff like that about this function, and really kind of having an understanding of sine functions and all these shifts. And if that's not something you feel comfortable with, 100% make sure your calculator is in the correct mode, which it should be in radians, and evaluate. Take in your calculator, type -2 times sine of pi divided by 6 times 3 minus pi over 2, close parenthesis, plus 3. And then replace that 3, that you replace the x with a 6, and then replace it with a 9, then a 12, then a 15. And your calculator will give you all of these exact same values. These aren't something that I'm making up here special, and your calculator is going to say something different. So if what I talked through here, the kind of this reasoning idea behind all of this, doesn't make sense to you or really kind of confused you, do not be afraid to rely on your calculator. That is 100,000% okay. All right. So let's graph this. So I know that we're going to go 3, 6, 9, 12, 15. Now, I know we are at 3, 1, 5, 3, 3, 6, 1. And we can get this nice little graph. Okay. One thing that I've seen a lot of students do, and I kind of have the same issue right now going on here. Peak. Okay. So right here, our function is back at the midpoint, so it's going to continue down. But if you were to ever stop your function, say at this high point here, make sure that your arrow doesn't look like it's going up, like the function is just going to take off, because that's not what happens, right? So make sure that you kind of have a little bit of a arrow like that. So if you're drawing these, make sure that your arrow represents, right? If we look over here at the right-hand side, after 15, an arrow kind of curls up to symbolize that this function is going to curl up and continue this pattern. If I had that arrow just pointing down, it would look very much like this function just shot down. Okay. All right. There's that. Sine and cosine functions. Now we're going to talk about tangent. So y equals tan of x is an odd function. So that means that the tangent of x has functional symmetry that is odd. What that means is it has a rotational symmetry with respect to the origin. If you were to take a piece of graph paper, graph the tangent function perfectly, put a pin at the origin, you could spin that paper around 180 degrees and it would look the exact same. Okay. So that's what this means. Now, because of some of the things we talked about in the last couple sections, we know that we can define tangent of x to be sine of x over cosine of x, which is really kind of cool, right? What's really cool is then from the unit circle, we get that the tangent of x is y over x, which is really nice. And so what this means, because this is a fraction, okay, this is undefined anytime our denominator is 0, right? We can't divide by 0. So this is undefined anytime the cosine of x is equal to 0. And that happens anytime x is things like negative 3 pi over 2, negative pi over 2, pi over 2, 3 pi over 2, and so forth. Okay? I mean, it actually kind of dots in the beginning too. So what this means is we have a very unique domain for this. Now, our domain for this isn't something we want to write using interval notation because it has an infinite number of breaks, gaps. And so we're going to use what we call set builder notation. And the way we write that, so the domain is the set of all x's, and we put this bar here. And what that symbolizes is such that. So it's the set of all x's such that x does not equal 2n plus 1 pi over 2, where n is an integer. Okay? So that just satisfies this listing here. And so if n is 0, we get pi over 2. N is 1, we get 2 times 1 is 2, plus 1 is 3. So we have 3 pi over 2. And if n is negative, and the reason why we have to have this weird thing, it's not just, we don't want to just say like pi over 2 plus 2 pi or 3 pi over 2 plus 2 pi, which we could. That's just messier. And so we set it up like this. Now the range of this thing, if you guys remember the graph of tangent, we did it the other day. The range is actually negative infinity to infinity. We can get 0, right? 0 is just anytime sine of x is 0. And because at these points of undefinedness, we get these vertical asymptotes where our function either explodes off to infinity or down to negative infinity, we get everything here. Now, with this function, okay, we graphed it a little bit and we looked at it, but I want to graph just one part. Negative pi over 2, pi over 2. Use red because it's nice, colorful. So this is what tangent looks like, right? And what's crazy here is then afterwards, so if we were to continue drawing this over here, right, it would look like that, and over here, right, it would, that was terrible. It would look the same. And so our period is actually only negative pi over 2 to pi over 2, which means that tangent of x has a period of pi. Let's go red. I'm going to go red bold. Not 2 pi. Okay. So sine and cosine have a period of 2 pi. And so when we're calculating their period with that b, right, p equals 2 pi over b, that's why we have that 2 pi involved. But we're not going to do that for tangent because tangent does not have a period of 2 pi. It has a period of pi. And so we need to make sure that we are kind of aware of that. So I'm going to do this off to the side here. What just happened? There we go. Okay. Calm down. Okay. So everything else about tangent is the same as far as amplitude, phase shift, and vertical shift. The one difference is, so if we have tangent of bx, this has a period of p equals pi over b. Okay, so when you're calculating that period, that is how we do that. Okay. So let's look at this lovely function here. We want to graph y equals -2 tan of 3x plus pi. We don't know what's the period, what's the phase shift. Okay, the amplitude is easy, right? That's 2. We've gotten used to that. Now, the first thing I want to do with this, I want to rewrite this, right? Because our phase shift is the same way as it was with sine and cosine, so we need to rewrite this function. And so I'm going to do that, we get -2 tan of 3 times x plus pi over 3. That makes it really easy. So our period is pi over b. In this case, b is 3. And our phase shift, okay, remember it's defined as x minus c. So in this case here, our phase shift is going to be negative pi over 3. Okay. So to figure out our start and end points, we could kind of do the same thing. We know that tan starts at negative pi over 2, it ends at pi over 2. So we could do our whole, that whole rigmarole. But we could also just use our phase shift, that it's negative pi over 3. So it's moving to the left pi over 3. So if I'm at negative pi over 2 and I go backwards pi over 3, we do a little bit of algebra. Okay. And what do we get? Okay. Anybody Bueller, pause it, figure it out. I'm not going to tell you. I'm going to wait. You got to wait. Just wait a little bit. You can do it. Figure it out yourself. Come on. I'm waiting. I am really going to wait. I know it's annoying. It's so annoying. Come on. You can do it. All right, fine, I'll tell you. So our start point is going to be I know I'm really annoying right now. Well, my brain just completely blanked. It's going to be negative pi over 6. Okay. That's not right. Where's my brain? Yeah, that's right. Hang on. That's not right. Negative 5 pi over 6. My gosh. My brain just stopped functioning. Okay. And now our period is pi over 3. So if we take that value and add 1/3, we get to a lovely endpoint. Negative pi over 2. So what that means is it took our function from negative pi over 2 to pi over 2. It's shrunken it down because instead of our period being pi, it's now pi over 3. So it's kind of squished it together and it shifted it off to the left. And so if we look at what that graph would look like, okay, negative pi over 2, negative 5 pi over 6. halfway between there. So at these values, okay, we have these vertical asymptotes. Now, the normal tangent function starts down in the lower left, goes up to the upper right. However, this function has an a value of -2, so it's flipped. So it means we need to start up here and go like that. And if you wanted to, you could continue to graph more of these, right? So then we would have -pi/6 would be our next asymptote. Come through in the middle. We'd go much like that. Okay. Because I don't want to do too much with this, because it's not as important as some of the other things we're going to be doing. We've already covered a lot this week. You know what? It's always more fun to do this in a fun color. Let's go galaxy. Let's make this big. Skip. So we're going to skip everything else on here. These graphs are just very tedious and unnecessarily challenging for no reason other than they're just messy, right? Tangent is already messy enough, giving these vertical asymptotes, but it is an important one to know because tangent is a function that we are going to utilize. And so we need to be aware of kind of how to work with it, especially if you can, subtract, things like 1/2 and pi/2 and pi/3. So make sure you guys are aware of how to deal with all of these. Find amplitude, period, phase shift, vertical shift, identifying the correct period, whether it's sine, cosine, or tangent, right? Remembering that those have a slight difference. And you guys will be golden. Now, what we're going to do is we are going to have a nice challenge problem, a nice extra credit problem. And I'm going to post that for you guys here shortly. It is to use these functions to model the Eye of London. So I'll post that and I'll make an announcement for you guys. And I'll let you guys know that that's out there. Without further ado, have a great day. And I'll see you guys next week for section 6.6.